So I spoke at J Spring, I think it was, a few months ago, and I was quite lucky because something interesting was happening at the same time. And so I just had I had a very few dedicated fans come to my talk, and so I scored really high, with the result that they invited me back, which I was quite surprised by. So thank you for coming. I hope that this is not going to be a complete waste of your time. All right, let's have a look at Java 9. Now, you obviously are all excited and happy that Java 9's been finally released, with bugs, of course. For example, I'll show you a piece of code. No, I won't show it to you. I will show it to you later. So, of course, we've got bugs. We've got bugs in all versions of Java. But there are some really compelling reasons why we should move over to Java 9. Like always, there's always the temptation where you can get all this cool stuff, but you have to pay all this money, or this price, or this effort to get to this new stuff. So Mark Reinhold made these goals for Java 9. And I won't read them because they are, text. I don't like reading text. Very, very wordy. But basically, number one was it must become smaller. The JVM must become smaller. Which is really important because, Java runs on all these smartphones nowadays. Oh, no, wait a minute. Okay, it's useful for like Docker and stuff like that. But besides that, if you're running like what a lot of people do with big monoliths, you don't really care how big the JVM is. It could be 100 gigabytes, you wouldn't care because it's like on the server, boom, plonk it on there, forget about it. But of course, for Docker and microservices, we do care about the size of the VM. But small computing devices is not really what we're trying to do with Java. At least I'm not. I don't know if you are. The second part, which they really wanted to push, was to improve the security of Java. And to me, that's really the main reasons why we've had this pain of going to modules in Java 9, to improve security. Because there are a lot of things that you could do in the past which would break, which would shoot yourself in the foot. Basically, they would give you a gun without a safety catch and no holster, so you put it in the, in your trousers and lose parts of your body. And so, never mind shoot yourself in the foot. It was much worse than that. And the third point was to improve application performance. Yeah, of course they would say that, right? So I don't know if you'll see a noticeable improvement if you go to Java 9. Now, this wasn't true in the past. In the past, we went from Java 1.1 to 1.17 when we had all of a sudden had the just-in-time compiler. Our code ran twice as fast. Now, that's a performance improvement, right? And then we went to the generational garbage collector, and then again our performance improved by a significant amount. You could actually measure the difference. You could see, oh, no, this is amazing. And hotspot profilers really make it a big difference. So you will see an improvement in some things that you do. But of course, they would say that it would be faster. Otherwise, why would you go to the pain of going over? And then the last one is it's going to be easier to develop and maintain. Yeah, of course, again, they would say that, right? But the only one that I think is really compelling and convinces me that this is something we should be looking at is number 2, about where we are going to improve the security. Now, I want to take you in a small path from what we had to what we have now and to see how you can still break things today. Now, Java has always been, the dream was that it's 100% safe, that you can't hurt yourself. It's the sandbox. For example, how many of you have got a security manager running when you run your application? One person. That's a new record. A new record. We've got one person in the room. Very good. Most people don't. Most applications run without a security manager. And I remember 16 years ago, I taught a course in Mauritius. It's an island in the Indian Ocean. And they asked me to talk about Java security, about security managers and how to set them up. And I spent a lot of time figuring it out. And after that, no one's ever asked me again, how does it actually work? How do you actually write a proper policy file? If you Google for policy file, all you'll find is blah, blah, allow everything, right? And then a comment saying, you wouldn't do this in production. But basically, we've had the security managers, we've had the security policies, all that stuff, for a very long time, at least the last 16 years, before that even, 20 years. But we haven't really used them. It's like, you've got a lock in your house, you never lock it because, well, why would you, right? So Java was supposed to be secure, and a lot of things that we, in the beginning, if we wanted to do really nasty stuff like compare and swap, we had to go down to JNI. And then at some point, I'm not sure exactly when, it was either Java 2 or 3, maybe even 4, they introduced Java sun.mis.unsafe. Now, if they'd called it something like sun.corber.anything, like .boring, blah, nobody would have noticed it. Nobody would have seen that there is such a thing as unsafe. But if you call it unsafe and you tell programmers, don't go there, then they all want to know how to use this thing, right? It's like you're really tempting people. And the idea was with sun.mis unsafe that this is only for the clever people, so not for you guys, right? It's only for the guys who write the JDK. Now, if you've seen the source code there, you know that that's not entirely, anyway. So only they are supposed to use sun.mis unsafe. And you can do things like create objects without calling their constructors. Now, I was looking at Unsafe today on the plane over from Crete, and I noticed one particular method where they use Unsafe to throw a checked exception in an unchecked way. It's inside class.new.instance. So if you've got a checked exception, they simply rethrow it with unsafe as unchecked. And that method, by the way, is deprecated in Java 9, which is, I think, a good thing. But you can do things like allocate large blocks of native memory. You can peek and poke into memory, compare and swap, whatever you want. It's very powerful. You can have fences. I already mentioned throwing exceptions unchecked. And somehow I find them a little bit bipolar, because all of a sudden they go and they say, you're not supposed to use unsafe in Java 9, but then they add a new method into unsafe. So, make up your mind. Pardon, sorry? Oh, for that new method. Oh, no. We've got somebody admitting guilt. So we've got a new method for releasing native buffers. I'll show you how that works a bit later. So it's and of course, when Java 9 was first released, they told us you will not be able to touch unsafe at all. And then they sort of relented and they gave us sun.mis unsafe, because there's so many classes out there that actually use it. Now, how do we get to this place where ordinary programmers who've got no business using a thing called unsafe use unsafe? Well, it started like this. In Java 5 and 6, we had a class called concurrent link queue. And concurrent link queue has had this thing called atomic reference field updaters. And it used these field updaters to update the item and the next inside the concurrent link queue. So this is like, in other words, instead of having an atomic reference pointing to item and another atomic reference pointing to next with all the indirection you have and the memory layout, costs and so on, you actually have simply a field updater that can update the fields with compare and swap and things like compare and set, all these different things. And so these field updaters had a problem. And the problem was that they didn't have much of memory as to the context of where they were used in. So you'd set them up, and then every time you called them, they would check whether you had the permission to actually do that update. And we asked them years ago, please can you change them so that they don't ask every single time? And we were told this can't be done. Of course, now it has been fixed, so now they actually are quite fast. But in Java 7, they introduced a new way of doing this internally inside concurrent link queue, which was with unsafe. And unsafe has got this lovely, unsafe.compare and swap object, and it basically allows you to do compare and swap on any memory location. It's got to be at least 32 bits though. And so besides having all the cool features now of being able to have it at zero cost, or maybe not zero cost, but not the cost of reflection, you can actually also other stuff like put ordered object, like, what's that? Oh, that's cool, that's good. Let's use that for writing queues. That's going to be fun. Okay. And then in order to access the memory location, you'd use point arithmetic. So you'd do something like, find out what the offset is into the object, with item offset, calculate that, and then use that to peek and poke into memory. And of course, you hope that you do this calculation correctly, because if you get it wrong, bad things might happen or do happen. So this is why it's called unsafe. You can peek and poke into memory and hurt yourself. So this is sort of how it works. And what they did in Java 9 was they wanted to clean up all this type of code. So to get away from this mistake of using unsafe. And it's a bit like, if your parents always speed or they always drive without a seatbelt and they tell you you must wear your seatbelt, you're not going to wear your seatbelt because your father's not wearing your seatbelt. And so, if the guys who wrote the JDK said, well, you have to use, you need to use unsafe here, then we will also use unsafe because that's what they use. And so they went through a big phase in Java 9 where they tried to get rid of all usages of unsafe. And so instead of unsafe, we now have VarHandles. Now, let's see how they differ. With unsafe, you take point arithmetic, you work out where in the object your field is, what's offset from the beginning, and then you peek and poke into memory using that. But you could put any long in there, so you could write anywhere into memory if you wanted to. With VarHandles, it's a lot more controlled. So with VarHandles, what you would do is you would first of all you'd have your item and next as volatile fields same as before, and then you define a VarHandle which would be called something like item. We normally make it capital letters off the actual field that we are trying to protect. So the item will be protecting the field item. Capitals is protecting small the field, and then the way that we construct these VarHandles is we make a method handles lookup, and the lookup then finds out from what context you are trying to modify and read and write this field. So it can test once off when you first construct it whether you've got the permission to actually do this or not. And after I've made a method handles lookup, I can then say find VarHandle. I pass in the name of the class, which could also be an inner class. It doesn't have to only be the one class. The name of the field and the type of the class, which is in our case, because it's a generic, it's of course is an object.class. And typically what we do is we catch reflective operation exception. If anything goes wrong, then we throw a new error and rethrow that. So this is how you'd set up your VarHandle, and then you can do all sorts of cool stuff with that. Now, in Java 7, you can see that the biggest, one of the biggest, the biggest user of VarHandle, of unsafe, was actually Java concurrent. And that's the one that they targeted to get rid of from Java 9. This is Java 7, Java 8. It looked very much the same, except that, of course, concurrent increased usage of unsafe. And they said, well, this is not safe, so let's try and reduce it. Let's try and make it less. And so in Java 9, they stripped that right down to almost nothing. But, due to the way that they changed the way that buffers worked, Java Nio increased, but it's an artificial increase. It's not something that is relevant to our particular problem. And Java Lang, there was something there. I looked at it early on today, but it was. I woke up in a daze because I woke up really early to get here, so I don't remember why Java Lang was so high. But the important thing is that Java concurrent is now very low. It's much, much lower than it was before. And don't forget that Java concurrent also includes your atomic classes and atomic, different locks and so on. So it's pretty good that they've got it down to only 8. So that's a really good example. So what can you do with these wonderful things? Well, you can shoot yourself in the foot in a new way, all right? Because in the past, we basically had 3 different ways in which we could access fields. Either just the plain reading and writing, or there was the volatile reading and writing, or there was the put ordered, the lazy set, the lazy get, those types of things. But now we also have get and set opaque. And get and set opaque is a new way. It means that eventually you will see the change, right? Eventually. Eventual consistency. So sometime in the future, you will see the change. Now, it doesn't say when. It could be the next nanosecond. It could be the next minute. It could be the next hour. You don't actually know. So you can't really use get and set opaque for any sort of inter-thread communication. So you can't write a queue with get and set opaque. They do use it sometimes, but the one thing it does do is you won't, for example, have you'll have an atomic write and an atomic read. So if you're writing in a 64-bit value, it will be written atomically. You won't have sort of two halves of the 64-bit value written in different times. And there's some other things as well, but it's sort of, if you try and write clever concurrent structures for inter-thread communication using get and set opaque, you'll get yourself hurt. And it might work on your machine, but it will probably not work on other machines. So probably want to avoid those. And then what's also interesting is you can get and set plain, so you can get and, even if the field is actually marked as volatile, you can still say that we're not going to have any volatile field semantics on that. Bunch of fences as well. And if you want to know more about how to use these, there's an article here by Doug Lee and his pals from the Concurrency Interest Mailing List, which you can read. Okay, now, I want to show you some interesting places where these things are used. And I want to look at just a little bit at Stripe 64. Now, Stripe 64 is a class which is used by long adder and long accumulator. Both of these classes use Stripe 64. And it basically allows you to update in parallel a number. If you take a normal number, like an integer or long, and you try and update it concurrently, you're going to have to lock. You have to have a synchronizer around that to make sure you don't have lost updates. And if you take an atomic integer, you don't have to lock, but if a lot of updates happen, you end up with contention on that, and you end up with having lots of failures and having to repeat, lots of CAS failures, compare and swap failures, and you have to redo the work. So you also get quite slow. And this is the reason why the concurrent link queue, for example, doesn't actually store the size. If they had the size in an int or inside an atomic integer, every time that you change the size, you'd have to touch this one field. We call this a hot field, so lots of different threads touching this one field. And what they wanted to do is to actually avoid having a bottleneck on the link queue. So if you say a size, they go and count how many elements are there. And there's been talk of now putting the long adder into the concurrent link queue, so that because with the long adder, you actually have got a pretty decent implementation that does something called lock striping to avoid having clashes or to minimize the amount of clashes. Now, the way that it works is that internally it contains a cell array, so the array of cells, and every time you update it, you increment it or you add, it updates the cell for that thread. So when you say get the value, then it does an accumulation, and it works out what the value is on over all the cells. So it's really fast to change it. To read it is a little bit slow, but we're going to most likely be updating more often than we read. Now, the maximums, first of all, the cell array starts off as just a single cell, and as each time you get a CAS failure, a compare and swap failure, it expands the array. It expands, and the maximum it will make is a square root of 2, a power of 2, power of 2, bigger than the number of, or bigger or equal to the number of hardware threads you've got in the system. So, for example, on my laptop, I've got, I think it's a square root of 2. It's actually, yeah, okay. So, for example, my machine, I've got 8 hardware threads. So it'll make 8 cells. 2 to the power of 3 is 8. If I've got a 72 hardware thread machine, it's going to make 128 cells. That's the maximum it will go to, expand to, up until the nearest power of 2. So it's limited by runtime.available processors. That's what it's limited by. And what's also interesting is that they mark these cell objects with something called @contended. Now, there are a whole bunch of tricks that we can use to do our own contended, and if you want to look at some really clever code, look at the black hole class inside the JMH benchmarking tool. That'll give you a very good idea of how to do this contended by hand, not let the JVM do it. Now, what's interesting is that that a thread is allocated to a particular cell, so and that they want to know where the thread goes really quickly. So the question is, how would they allocate threads to cells? Any suggestions? What do you think? If you wrote the code, please don't answer that. So how would we put a thread into a cell, or give a cell to a thread? Okay, so we do like a hashing. We take some attribute of the thread, and we use that hash in order to get a hash into the number, right? So this also will explain why we need a power of 2. It's going to be hashing, so it's some type of hash that gets you there. Now, absolutely right. Some bit mask. Now, they actually use something from thread local random. Now, okay, now you're going to see some really weird code going on, because thread local random in Java 7 was based on the thread local class. Right, so thread local was implementation. And it meant that every thread would have its own instance of thread local random. So what you would do is you would take thread local random dot current, and then you'd work out your random values. And it's much faster than math.random, or even if you make a new random object, this is much faster. And so we want to use the thread local random as much as possible. But with thread local random, even though it was much faster than math.random, it wasn't as fast as it could have been, because when we call current on the thread local random in Java 7, we have to do hash map lookup every single time. And this, of course, slows you down. And so what people do is they would then actually store the thread local random instance, and if you have a leak of that, then you end up having a thread local random instance, which is not, again, thread safe. So you don't have so you might have multiple threads getting the same random values, which, okay, who cares? But anyway, it's random anyway. Who cares if it's the same number? But they wanted to get this right. So what they did was, in Java 8, they basically made thread local random into a singleton, and the fields that they used to store inside thread local random, they now moved into thread. So thread itself contains all the values for thread local random. Let's have a look at some code. So if you go to thread test, for example, if you take thread and look inside thread, you'll see a bunch of values that are now stored inside thread. So you've got, for example, thread local random seed, random probe, and random secondary seed. Okay, so you were absolutely correct that they're using an attribute, but probably not the attribute that you thought they would be using. Okay? The attribute that they used for cell 64 is actually this thread local random probe, because the way that the probe works is some mathematical function that separates the numbers quite well from each other, so that you can get a very good hashing function of these numbers. So now the cell 64 needs to, or the stripe 64 needs to somehow get hold of this thread local random probe from thread. How does it do it? Well, remember when we looked at VarHandles in the beginning, you can only get VarHandles on your own class. Now, in the first versions of Java 9, the beta versions, we had one hack where you would have this master method handles lookup that could do anything, right? So you could look at any class with this method handles lookup. And for some reason, people didn't think that was very safe. Don't know why. Anyway, so instead, they introduced a new mechanism in Java 9 called private lookup in. In other words, you can now get a a volatile on a private field. So in Java 9, they don't want to use unsafe, but they wanted to use VarHandles. It was one of the last remaining places where they were using unsafe. And instead, what they now do is they take stripes, they use a VarHandle in order to get direct access to the field inside thread. Right. So of course this is a bit of a hack, and you can abuse this hack yourself if you want to. As I said, you can shoot yourself in the foot very nicely in Java 9. Let's try it out to see what happens when we change strings using VarHandles, right? So there's a thing called method handles of private lookup in. And in Java 9, we'll do the following. We'll say hello. So this font is small, but this font is big enough, I think. So we'll take, for example, we'll make a VarHandle. We'll call it value. This is going to be the value inside the string class. Right? You shouldn't be able to do this, but you can. So we'll need to get a method handles into a string. Normally you say method handles dot lookup, right? But that only gives you the context for my say hello class. I can't go and hack into other classes. So instead I'm going to say dot private lookup in, and I want to go into the target class, which is going to be, let me just go and make this into this lookup. Oh, no, this is too small. No. Okay. So it's going to be string.class, comma, method handles dot lookup, like so. And this gives me gives me back a lookup, so it's going to be method handles dot lookup. And this is going to be lookup into string. So this is how I get a lookup into the string class, which is private. And what I can now do, what I can try to do, it won't work, but we can try to do it. We can say value equals lookup equals. Ooh, it's so quiet now. Lookup into string dot find VarHandle, and we're looking on the class string.class. The name is value, and the type is? Pardon? Ah, you're too clever. You guys are too clever in Holland. In Java 9, it's a byte array. In Java 8, it was a char array. In Java 6, it was sometimes a byte array and sometimes a char array, depending on the day what it felt like doing. So it was very confused. So you're absolutely right. So it's a byte array in Java 9, which means the maximum length of strings is now shorter in Java 9, if you've got any funny characters which are not Latin 1, right? Like Greek, for example, you can't have such long strings anymore like you could do in previous versions. So let's throw a reflective operation exception over here, okay? And so we've got this value. Now we can just simply say value.set hello, comma, cheers, okay, byte array, can you get a byte array? Okay, we'll just say value.get over here. .get of cheers. And this way we're replacing the contents of the string hello with the contents of the string cheers. And so if we afterwards say hello, then it will say, what will it say? No, it won't work. You see, it won't work because, okay, no, because this is, of course, I must just comment this out, and this out, so it compiles. It won't work because in Java 9, the one thing they've done, which is actually quite good, is they've made it that you can't change final fields with VarHandles anymore. Right? So you can change final fields with unsafe or with reflection, but you can't change final fields with VarHandles, which I think is a really good way of doing things. So this will actually fail with an unsupported operation exception because the value is final. So what we need to do is we need to get the value of cheers, and we need to get the value of hello. All right? So hello. And then we're going to say system.arrayCopy from the source, which is going to be cheers, position 0 to the destination, which is hello, 0, array.length, get length it doesn't matter, they're the same length anyway. This only works because chairs and low are the same length, right? Don't take photos of this, no, don't take pictures. This is not, you shouldn't be doing this, right? And, okay, I must comment out this part here. And now when I print out hello, what comes out magically is cheers, okay? So I've changed the contents of the byte array that's inside there. So you can do the stuff, things that you really shouldn't be doing, you can still do. And the cool thing is that the cost of doing this is so much less than if you do it with reflection. Because reflection, you have to have all this cost of, security managers and stuff like that. That all goes away. It's like into the memory location. It's really great. Now, the only catch here is, you've got this wonderful feature, but I mean, who likes this stuff? Warnings. Nobody likes these warnings. So that's of course an annoying part because you don't want people to see these. So you can turn this off quite easily with just add opens, right? Now there was another setting they had which they took away, which was like just allow everything. But when you say add opens, when you run the code, it takes away these warnings. And what you're saying is you're saying there's a module called Java Base. And Java Base says exactly who's allowed to see it, who's allowed to use it, and who's allowed to do deep reflection on it. Because what we're doing here is something called deep reflection. We're changing values, we're using values and accessing fields which are private. And when we do deep reflection, what we're saying is that from normally, the module will have to say who can do that. And what we're saying is, well, we are also going to be allowed to do it. In fact, anybody can do this now. Anybody who's not inside a module can do this because we've said it's going to be all unnamed. So when you run it with that, with this little setting here, then that warning goes away. So I'm going to just copy and paste that because I don't like typing all this stuff. And of course, in the real world, you'll be having your values inside your systems inside modules as well, so you wouldn't be in the unnamed module normally, but anyway, here you can see it pops out without any warnings. Now, they tell us they're going to get rid of the setting in Java 10, right? Yeah, you're nodding. You're very optimistic. I like that. We'll see, right? We'll see if it really is going to be gone in Java 10. It should be gone in Java 10. It should have been gone in Java 9. But unfortunately, we need this private lookup in because well, it's used in a lot of different places, right? Let me show you. It's used in, find usages. Yeah, it's used basically in one place, which is in Stripe 64. So this is the only place it's used, as far as I can tell. But now I've got this big gaping security hole, so we can now access private data inside other classes. There's lots of fun. Okay. Now, just very quickly, I've got this giveaway. I publish mini courses. This one is normally €60. It's sort of Java 9 using Java 9. Some Java 9 features, some cool stuff on that. If you subscribe to that, you also get a subscription to my newsletter, and it expires in of this talk. So if you don't get it by then, it's offers off the table. I'll show it again at the end of the talk as well again. But I've got a whole bunch of different courses there as well. Okay, now this other thing that I mentioned was this unmapping. Now, we've always been able to map, well, not always, since Java 4, been able to map files into memory. So this is a really cool feature. But what we've never been able to do is to unmap these things again. We have to wait for the garbage collector. And one of our big things we try to do is to avoid full GCs. And sometimes a full GC is the only thing that's going to actually clean up and unmap the map byte buffers. In fact, the direct byte buffers. So this is something which we need to be aware of. So if I, for example, have a random access file here, and I make a file channel, and then I map it, you can close the channel, you can close the random access file, but that doesn't unmap the map byte buffer. The map byte buffer gets unmapped through a phantom reference, and there's a special class called a cleaner that is a subclass of phantom reference. And this cleaner, is used to eventually, once the phantom reference is released or is collected, then the cleaner can be used to unmap this map byte buffer. So in Java 7 and 8, if you wanted to do a random access file, you'd do something like this. You'd say, let's make here a class mapped unmapped test. And we're going to say try random access file, raf equals new random access file, now, file dot comma rw. We also make a file channel, and both of these are auto-closable, which means we can stick them into a try with resource. File channel equals raf dot get channel, and then we can say mapped byte buffer buff equals fc dot map read write 0,1000. So we make this map byte buffer that is for the first 1,000 bytes inside your file, and it maps it into memory. So now you can't put this map byte buffer into the try with resource because it's not auto-closable. The only things you can put in here are auto-closable, and you can't close it. You can only close the file channel and the random access file. You can't close the map byte buffer. And you also can't unmap it. So I've written a little class called console. There is another class called console, but that one doesn't work with an IntelliJ, so that's why I use this one. It just basically does this, buffered read inputs from reader and reads, nothing special. And what you can see is if I run this, I've exited the try with resource, and if I let me connect with. In fact, let me connect with something else. Who knows Java VM? Anybody? Yeah, it's gone in Java 9. So Java VM, and by the way, if you're using a Mac, and it takes 10 minutes to connect to the process, to find the process, there's a workaround to fix that. Okay, so what you do is you go, there's a plugin that you can use, available plugins called Buffer Monitor. Okay, Visual VM Buffer Monitor, and this one shows you what buffers you currently are using. So let me just close this and reconnect it again. I think that I didn't do it. Let me just do that again. So plugins, and the available plugins is the Buffer Monitor. Install. Next. I didn't click on that. Accept the license terms. Yeah, okay. And once it's installed, then we can reconnect to the process. And I'll zoom in now. And they've got the buffer pools. So you can see this is now, it's using a map byte buffer of 1,000 bytes. See here? And even though I've exited the try with resource and I've closed both the file channel and the random access file, the byte buffer is still mapped. Okay. So if I go back here and I'd actually do a force a system GC. So let me see. I'll print out closed, and then I'll print out system.gc. So I'm forcing a system GC. Let's run this again. So it's closed. We can see that. If I connect with Java VM now to this new process, and the buffer pools, you'll see it's still at 1,000. But I've exited the try with resource. So if I call close, it should if I call system GC, it should actually collect it. So if I press enter here, yeah, sometimes this doesn't do it because for some reason. Okay, sometimes my process doesn't work properly. This console is a bit buggy. Not my code, IntelliJ. It's a bit buggy. So let's open that again. This one here. And now the buffer pools, it's still there. So it's not very reliable when it gets cleared. You'd have to sort of set it to null and then call system.gc, because if you look at this code here, even though it looks like this is a code block, that's really a figment of your imagination, right? It's not really, that isn't really there. If I put this into a method, use buffer, for example, then it will actually collect it. Okay, I won't try this out again. Now, if I wanted to manually unmap it, the old trick that we used to use, which is horrible and very dangerous, you can shoot yourself in the foot with it, is the following, is you actually do this. You say, buff, you take buffer, you cast it down to direct buffer, which is a sun.mis class, sun.nio class, I think. And then there's a method called cleaner on it. And then on the cleaner, you can say .clean, because you get back the cleaner instance. And this, of course, is a real mess. I mean, you should never do this. But it does work. So let's run this. This is in Java 8. And it says close, but close doesn't have an effect. So let's open this process again. And buffer pools, you see it's still at 1,000. So it's still using 1,000 here. And now if I press enter, no, it always puts it in the wrong place. Okay, now, let me try that again. This console really is buggy. I think it's because I put my mouse cursor in the wrong place. Okay, now it should be gone. So it's actually released that memory manually by downcasting to a map to direct buffer and then collecting it. So if you look at the buffer pools, you see memory use is 0. Okay, but this is incredibly dangerous. You should never do this because what if somebody doesn't realize that it's been cleaned and uses it afterwards? So, for example, he says, "Oh, this is fun. I'm going to say put int 42." Now, the results are undefined of what might happen. So this presentation might be over after this run, right? So let's hope it doesn't destroy everything. Yeah, and that's what usually happens. Usually it just does a core dump, segmentation violation, because I'm writing to memory that doesn't belong to me. So this is why they don't allow you to unmap it. Now, for this actually was a coding pattern which was quite common, sadly speaking. And the cleaner was something that everybody wanted to use. So they brought the cleaner into Java 9. Let me just copy this over. They brought the cleaner into Java 9, but they didn't. They gave us a different cleaner to the standard cleaner. The way that one needs to do this in Java 9 is no longer by downcasting, but there's now unsafe.getUnsafe.invoke cleaner. You see? Java 9. So a new method. Yeah, guilty party at the top there. There we go. Waving to me. Invoke cleaner, which does the same thing. It does a few more checks than we did. It makes sure it actually is a direct buffer that you can clean it, and some other checks to make sure. But anyway, and of course, if you try put int afterwards, it will still give us a segmentation violation and die, or not. Depends on if you're lucky or not lucky. Lucky is if it crashes, right? That's actually lucky. So there we go. Lots of fun. Of course, you have to first get hold of unsafe. I won't show you how to do that. You can figure that out yourself. Now, what I mentioned just now is that Visual VM is gone in Java 9, which is a great pity, I think, because I quite like the tool. I'm sort of used to it. And we still have a bunch of other tools. And you can actually use Visual VM separately on GitHub. So they've got it there too. Also, xrun hprof is gone. Xprof is still there for now. But something which is quite interesting is that they are on the path to open sourcing Java Flight Recorder and Java Mission Control. So that's sort of we're looking at March, April. Next year, that should be open sourced. And I think that's a good thing because I haven't spoken about Java Mission Control or Flight Recorder like ever because it was a trap before. It was a trap. You see, because it was commercial and there was no price tag, you didn't know what you'd pay if you used it. You could unlock commercial options, but you couldn't. Once it's unlocked, you'd have to restart the virtual machine to turn it off again. So it was quite dangerous. You could use it for free in development, but not in production. And this gave big problems because once you get used to using a particular tool, it doesn't matter how bad it is, you're going to want to use it later on when you need it, when you're facing an issue. For example, I use VI every single day of my life, right? Doesn't matter that it's a terrible editor, but I still use it every day because I'm used to it. It's not that bad, actually. But now, something which I tried to do a while ago is I tried to make my own fields contented. I mentioned contented with striped 64. Striped 64 has a very high chance that all the cells get allocated in the same cache line. And we don't want to do that because that means that the cache will, if you write to one of the cells, all the values will be written out. So we want to, sometimes we want to use this thing called contented. Now, contented used to be in sun.misc. They've moved it into jdk.internal.vm.annotation.contented. So it's moved into an internal package. And I struggled for a while to figure out how to do this. And it really shouldn't have been so hard. I mean, it just says, error. It doesn't compile because it's not visible. And it's all about modules and getting the modules right. And basically, if you want to use it in your own, if you want to use contented yourself, you can do that with add exports. And again, what we're doing is we are externally modifying the module structure. We are saying that even though we aren't one of the users, official users, of this class, we are still allowed to use it. Now, add exports doesn't allow you to do deep reflection like add opens does, but it does mean we can compile against it. So it only makes sense to compile against add exports, not against add opens. And then when you run it, you would say -xx colon minus restrict contented, and then it would also use your class. It would use it for your classes as well, not only for system classes. Now, of course, you don't want to make everything contented because every time you mark a field contented, it increases the size of that field to 128 bytes, not just like 4 bytes for an int. It would be 128 bytes for an int. So it's much bigger than you probably want it to be. So add opens versus add exports. Add opens allows you to deep reflection on elements like I did with string, whereas add exports allows you to access public classes. So they're public classes, and in the past, you could access any public classes and any public fields and any public methods in Java. But since we've got modules, they've now restricted that. But you can say that you want to be able to do this anyway. And both will be removed in future versions of Java. They promise. With unsafe, also be gone. They'll be gone, and everything else. Will be completely safe. But we'll see if if it really happens, because programmers are quite annoying. We really complain about everything, and if you take away our toys, even though if the toys are dangerous, we still complain. Okay, what other cool things? Well, we've got some new features for streams, right? We've got a method like take while with a predicate and drop while with a predicate. And these look amazing because, I remember when I first started speaking about streams, somebody asked me, how do you do that? And I asked Brian Getz, and he said to me, well, you don't want to do that. And I said, why don't you want to do that? He said, well, how would you do it with parallelism? And that's a good question. How do you do it with parallelism? And the answer is, it doesn't work that well, necessarily. Your results, your mileage might vary, right? So it might work, or it might not work at all. You've got to be actually quite careful with this, right? And I did some tests with it just to play around with it. And in the one test, the normal sequential test executed fine, within a reasonable amount of time. And when I did the same thing with parallel, it ran out of memory. So you need to be careful here because there's not a very clear mapping from sequential to parallel here. Most of the time, there's a very clear mapping, but not in this case. All right, now, another cool little toy, JShell. When I first saw it, I thought, well, this is going to be completely useless, but it's maybe not completely useless. Maybe it's useful. Okay, I started recording a course for newbies, for people who, because my niece in South Africa wants to learn Java. So I thought, well, she doesn't know programming, so where do you start? And I don't want to start with public static void main, right? I don't want to start with that. I want to start with what's 3 plus 4? What's 2 billion plus 2 billion, right? I want to start with that and get to understand bits and numbers before we go into semicolons and public static void main. What is static? What is an array? I don't want to start with that stuff. I want to start with simple stuff. So I traveled to Bucharest a week ago, and on the way back, I thought, you know what, I've got some time at the airport. Let me start recording a course. So I've started recording this. It's called Juppies. It's on my website, and it's free, and it's there just to try it out. How well you can use JShell for teaching programming to people who've never programmed Java before. So it's challenging, some of it. And a few things to get this to work. You should set up your editor environment variable to point to your favorite editor, text editor, so that you actually get your your normal editor that you're used to. The default editor is some weird thing that I don't even know how to use. Also, the startup is quite slow. And the reason is that there's a whole bunch of compiling of the AppSec syntax tree in the background, and I'll demonstrate that to you in a moment. Once it's warmed up, then your execution speed is Java speed. So it's actually not slow. JShell is not slow. It's just the startup speed is slow. Right? Once it's going, it's going to beat the pants out of just about any other scripting language out there. And I'll show you a few things. Another thing is that with JShell, you can actually build a script like a bash script. Now, normally with a bash script, you would start your script with hash dollar and hash exclamation mark, and you point it to where the path to your bash is, and then bash would be able to run it in the command prompt. And you can actually do that also with JShell. So what you do is you'd start with a comment, and we put $Java home /bin/JShell. Now, there are a few tricks to get this to work. The first trick is, by default, JShell doesn't return a number, or it always returns 0 from the script. Now, if you know anything about Unix script, you want to be able to return a number that indicates success or failure, right? And you can't do that by default with JShell. If you say return 1, it's going to say you can't return anything. It's a public static void main. You can't return anything. And if you say system exit, it also doesn't allow you to do that either. So you can actually, if you say minus execution local, then system exit works and it returns the right number. And then you'd say, the rest of that, I've also got a little file called exit.jsh. And so let me show you how nicely this works. This is this one here. Okay, so I've got here a file called hello world, right, with my script at the top. Let me just delete this like that. And at the end, let's say system exit note to say that it was successful. And then I can say hello world like that, and if I've got Java 9 on there, and it goes and it runs it as a script. Hello world. Isn't that cool? How cool is that? And it exits at the end. And the reason it exits is I've got another file called exit.jsh, which just has /exit on it. Right? Now, normally when you start JShell, you can do things like let's make it 4 plus 5, right, or 4 divided by 5, whatever. You can write any Java code in there, and you can even say thread.sleep 1 second. And you don't have to worry about exceptions necessarily because it catches, it rethrows them for you without you having to do anything for it. So this is pretty neat. And then /exit or Control-D at the end closes it. So this is some of my. Now, what's interesting about this hello world is how long it takes to run. I don't know if you noticed that. If I do time hello world, it took 3 seconds to run of real time to print out hello world, And it actually took 11 seconds of user time, right? So why is there such a big difference between user time and real time here? Any ideas? Exactly. So when you run this again, let's run it, and you do control \, you can see that they've got a whole bunch of compiler threads that are compiling the abstract syntax tree in the background here. So there's define class and a whole bunch of things happening in the background. Some other changes. In Java 8, they deprecated incremental GC, incremental CMS, and they got rid of it in Java 9. In Java 9, they deprecated even CMS. So now, going forward, we need to use G1 for the type of things we used to use CMS for. And it's very easy to configure. You simply set the maximum time, the maximum heap, and you're done. Well, that's not quite true, but that's at least the propaganda from Oracle. It doesn't really work like that. Do we have time for one more thing? Not really. Okay. I'll just mention something. I won't show you how to do it. And that is, it's in the slides how to do it. You can actually change, in the past, if you wanted to change the way that something worked, like for example, big integer, you could simply use the boot class path to pull in a different big integer into your system, right, in Java 8 and before that. So boot class path was your secret to do this in the past. In Java 9, there's a whole bunch of things you need to do to create the same effect. So what you need to do in Java 9 is you first have to compile your changed big integer, if you want to, for example, make the square method public. The second thing you've got to do is to compile your code against the patched big integer. And then the third part is to run your code against the patched big integer. Now, we'll make these slides available. This shows you the 3 steps you need to do to achieve the same thing as you could do before. And it will always be possible to do these things. But of course, it's a bit more work now that we've got modules.